Okay, we're looking at the last topic here in Unit 8. We're going to talk about this thing called absolute or conditional convergence. So when we look at a couple different types of series, and you can read this, but the short of it is if you have a series that converges, there is a possibility that it doesn't always converge. When we take away, like let's say for instance an alternating series, when we take away the fact that it's going between a negative and a positive value, it's going to grow if we take that idea away. So if we're just looking at the terms, are they going to do descend enough? Are they going to get small enough, quick enough for it to converge? So this thing, we need to take both the we need to see if the series converges as it stands and the absolute value of the series. So if it converges for both, then it's called absolutely convergent. If the original series converges but the absolute value does not, then it is conditionally convergent, or converges conditionally. Or we just have ones that are going to be divergent no matter what. So we'll take a look at three examples here in this video. All right, so if we look at the first series, we automatically are going to think alternating series because of the -1 to the n. So we have that. We look and we know that terms are decreasing. So we have that. Terms are decreasing. And we know that if we ran that limit, if we run the limit of 1 over n, as n approaches infinity, that's going to be 0. So this converges by the alternating series test. And now what we have to do is we have to look and we have to do the absolute value of this. So if we think about absolute value, we have 1 over n. So we're looking at the series of 1 over n. So we know this is going to diverge because of the p-series test. Okay, p being 1. So this is going to be converges conditionally or just conditionally converges, in whatever order you want to say it in, works. Okay, so that's how that's done. So you check the original and then you check the absolute value of that. Now the next one, a little trickier. First thing we need to do is look at the original. So actually let's we're going to do a comparison test. We're going to do direct comparison. So let's compare it to 1 over n squared. And if you think about it, 1 over n squared is larger than this series. So we can go ahead and say that 1 over n squared is larger. And we know 1 over n squared converges by p-series test. Okay, p is 2. So the original is going to converge because of the direct comparison test. So we can write that. Cosine of n over n squared converges by direct comparison. Okay, and then we think about the absolute value. So absolute value of, absolute value of cosine over n squared. So this is smaller, so this is going to be smaller. You think about that, because cosine is going to go between, your regular cosine goes between positive 1 and negative 1. If these are just between 0 and 1, it's still smaller than 1. So that's going to be smaller. So the absolute value converges by direct comparison test. We're still comparing it to this 1 over n squared. So if it's convergent both times, the absolute value and the original, then we can say this is absolute convergence. And then the last one, if we look at this, we have n to the e underneath negative e to the n. So this is divergent by nth term test, because top's going to grow faster than the bottom. So we know we have the limit as n approaches infinity, we would want to write that out, is infinity. So this diverges. So there's no need to do the absolute value of the original because this diverges. So there's no way it's going to converge with the absolute value either. So that is the last part of the section, so, or last part of the unit. So let me know if you have any questions on this or anything else. We're going to do some days for review, and then we'll look at the taking the test. So again, let me know if you have anything.